Welcome to our quantum deep dive.
Great to be diving in.
Today we're taking a really fascinating journey looking into the extraordinary legacy of Marie Curie.
An absolute giant of science.
Exactly. And our source material for this is a truly insightful essay by Jürgen Schneppat. It's titled Marie Curie, Wegbereiterin der modernen Wissenschaft.
Which translates roughly to Pioneer of Modern Science. A very fitting title.
It really is, and it helps us connect her pioneering work, to some very cutting-edge fields today.
Right.
So our mission really is to unpack how Marie Curie's foundational discoveries in radioactivity, how they actually laid the groundwork for concepts now central to modern quantum technology.
Yeah, the connections might not be immediately obvious, but they are profound.
That's it, revealing those surprising links and understanding why her story, her journey, still resonates so much.
Well, it's hard to overstate her significance. Marie Curie. She's just one of the most important scientists ever, full stop. And that unique achievement, being the first person to win Nobel Prizes in two different sciences, physics and chemistry. It's unparalleled.
Truly.
And what's key here, I think, is that while she wasn't directly working on quantum mechanics as it was being formalized.
Right. The theory came a bit later.
Exactly. But her discoveries, her empirical findings about radioactivity, they didn't just hint at a quantum reality. They practically, demanded it.
That's a great way to put it. Demanded it.
Think about it, a supposedly stable atom just spontaneously changing, emitting energy.
Completely breaking the mold.
It breaks almost every rule classical physics had. It forced scientists to confront this new reality where atoms weren't these tiny, indivisible, unchanging things.
Okay, so let's start at the beginning then. Her early life. Maria Skłodowska, born in Warsaw, Poland, 1867.
Yes, and it was a difficult context. Poland was under intense Russian political oppression at the time.
Right. But her family was educated. Her father, especially, he taught math and physics.
So that seed was planted early on.
It seems so. He really cultivated her scientific interest. But, as a woman in that era, formal higher education wasn't really accessible.
The doors were closed.
Pretty much. So she had to find other ways. She got involved with the Flying University.
Which was essentially an underground secret educational network, right? Incredible determination.
It really is. Then she moves to Paris in 1891, aiming for the Sorbonne.
And that came with its own huge set of challenges. She changed her name to Marie, had to grapple with French.
And the poverty. I mean, the stories of her fainting from hunger, the cold.
Extreme hardship. Yet her brilliance just shone through. Degrees in physics in 93, mathematics in 94.
Just remarkable given everything she was up against.
Absolutely.
And entering the scientific world, it was so heavily male-dominated.
Completely. An old boys club, essentially.
But her talent, her just sheer discipline,
Yeah.
It allowed her to carve out a space. She just refused to fit into the expected mold for women.
And in doing so, she didn't just forge her own path. She really did pave the way for generations of women in science after her.
Yeah, a true trailblazer.
And then came a really pivotal moment, meeting Pierre Curie.
An esteemed physicist in his own right.
Exactly. He became her husband, yes, but also her indispensable scientific partner. Their collaboration is legendary, one of the most productive in science history.
A real meeting of minds.
Truly.
So their partnership becomes central when she decides to investigate Henri Becquerel's discovery from 1896.
Right. Becquerel had noticed uranium salts emitting some kind of penetrating rays spontaneously.
And Marie took that observation as her PhD topic, basically. She started this incredibly systematic investigation.
Using instrumentation Pierre had developed, that electrometer.
Which allowed for really precise measurements, didn't it?
Crucial. That precision led her to a truly groundbreaking finding. She discovered the intensity of the radiation was directly proportional to the amount of uranium.
Okay, that makes sense.
But here's the kicker. It was independent of the chemical compound the uranium was in.
So it wasn't a chemical reaction producing the rays.
Exactly. That was the revolutionary part.
Yeah.
It meant the radiation had to be coming from the uranium atoms themselves.
Challenging the whole idea of atoms being indivisible and unchanging.
Precisely. It was one of the first major cracks in the foundation of classical physics, hinting at something going on inside the atom.
Wow. And then came the hunt for other substances that might do this, which led to that monumental effort with pitchblende.
Oh, the scale of that work is just mind-boggling. Processing literally tons of this uranium-rich ore.
In rudimentary conditions, too. Not exactly a modern lab.
Not at all. Grueling, painstaking physical labor, combined with delicate chemical analysis.
And that led to the discovery in 1898 of not one, but two new elements.
That's right. Polonium, named after her homeland, Poland.
A nice touch.
And radium, which was even more intensely radioactive than uranium.
And this is when she coined the term radioactivity.
Yes, she literally named the field she had just opened up. It fundamentally changed our whole understanding of matter. Suddenly, atoms weren't static. They could transform, release energy.
Which, as you said, classical physics just couldn't really explain.
It couldn't. How could this energy just appear? How could an atom change its very nature? These were the questions her work forced onto the scientific community.
So that brings us right to the bridge, her discoveries. How did they specifically feed into what became quantum mechanics? How did they defy classical physics in ways that needed a new explanation?
Well, think about spontaneous emission. An atom just decays. It spits out a particle, changes into another element sometimes. Classical physics is deterministic. You have cause and effect. This seemed random, probabilistic.
You couldn't predict when a specific atom would decay.
Exactly. And also, the energy release.
Mm.
Why specific types of particles with specific energies? And how could particles like alpha particles escape the nucleus? The electrical forces holding them in should have been, classically speaking, insurmountable.
Like a wall they couldn't climb over.
Right. But quantum mechanics later introduced concepts like quantum tunneling. The tunnel effect, as George Gemmell applied it to alpha decay.
Tunneling. So like punching through the barrier instead of going over it?
Sort of, yeah. It's a probabilistic effect where a particle has a non-zero chance of appearing on the other side of an energy barrier it doesn't classically have the energy to overcome. Curie's radioactivity was prime evidence for these kinds of non-classical behaviors.
Okay, I see. And her work also showed energy being released in these discrete packets, right? Supporting Planck and Einstein.
Absolutely. The specific energies of alpha and beta particles, the gamma rays, it all pointed towards energy levels within the atom and nucleus, towards quantization. It wasn't a continuous spectrum of energy being released. It came in specific amounts. This was empirical data backing up the theoretical work of Planck and Einstein on quanta.
So she was finding the puzzle pieces on the ground, even if the full picture of quantum theory wasn't assembled yet.
That's a perfect analogy. And the statistical nature of decay itself, the half-life concept she helped establish.
Right, where half the sample decays in a set time.
That's inherently probabilistic. We can describe the group behavior statistically using equations like small nt, but not the individual atom's fate. This is fundamentally quantum mechanical, not classical. It paved the way for understanding atomic decay, nuclear physics, fission, all governed by quantum rules.
And the Schrödinger equation you mentioned earlier, that's the mathematical tool to describe these quantum states and how they evolve.
Exactly. It's the cornerstone equation for describing how these wave functions, representing the particles, behave over time, including their probability of doing things like tunneling or decaying. Curie's work provided the phenomena that this mathematics would later explain.
It's incredible groundwork. And thinking beyond the specific discoveries, her approach, that interdisciplinary nature, mixing physics and chemistry.
Oh, absolutely crucial. She used physical methods, the electrometer for precise radiation measurements, alongside sophisticated chemical separation techniques to isolate tiny amounts of new elements from tons of ore.
That blending of fields seems very modern, actually. Quantum technology today needs that kind of collaboration, right? Physics, chemistry, material science, computer science.
It's essential. Quantum computing, quantum sensors, they all rely on manipulating materials and physical phenomena at the atomic level. You need chemists, material scientists, physicists, engineers, all working together. Curie's lab was, in a way, a prototype for this modern interdisciplinary approach.
And her stance on foundational research, not patenting radium, that seems almost unthinkable today.
It was a conscious choice. She and Pierre believed their discoveries belonged to science, to humanity. They wanted others to be able to research radioactivity freely.
To accelerate progress.
Yes. And it absolutely did. Imagine if access to radium had been restricted early on. It allowed the field to blossom much faster, leading to all sorts of applications. It speaks to a commitment to pure, open science.
And those applications have had such a huge impact on society. Let's talk about medicine.
Radium's effects on tissues were noticed early. This led quite quickly to the development of radiation therapy, or Curie therapy as it was sometimes called, for treating cancer. Still a pillar of cancer treatment today.
And her work during World War I. With the mobile X-ray units.
The petites Curies, yes. She didn't just conceptualize them. She equipped vehicles, trained technicians, often women, and went near the front lines herself to help surgeons use X-rays to locate bullets, shrapnel, broken bones.
Saving countless lives and limbs. Just incredible practical application.
Absolutely. Then in technology, radioactive isotopes derived from her discoveries are used in so many ways. Powering space probes.
Right, radioisotope thermoelectric generators.
Exactly.
Yeah.
Industrial gauging, sterilization, non-destructive testing, the list is long. And her techniques for precise measurement, they laid groundwork for the kind of sensitivity we need in, say, quantum communication or quantum sensing today.
Secure communication relies on quantum principles.
And detecting tiny changes using quantum effects. It all traces back to being able to precisely measure and understand these fundamental atomic processes she unveiled.
And then there's energy. Her work didn't directly lead to nuclear power plants, but
But it was the fundamental first step. Understanding that atoms contain vast amounts of energy and can transform. That led eventually to Hahn and Meitner's discovery of nuclear fission.
which then led to both nuclear energy and, unfortunately, nuclear weapon.
Yes, the potential was unlocked by that fundamental understanding of the atom that Curie pioneered.
Now, it wasn't an easy path for her, personally or professionally. We touched on the male-dominated field, but there were specific gender barriers, weren't there?
Oh, absolutely. The 1903 Nobel Prize nomination initially only included Becquerel and Pierre.
Seriously, she did the bulk of the experimental work.
Pierre had to actively intervene to ensure she was included. Then, the French Academy of Sciences repeatedly rejected her membership application.
Even after her Nobel Prizes.
Even after. And becoming the first female professor at the Sorbonne, taking over Pierre's chair after his tragic death. She faced immense skepticism, xenophobia even. Her persistence was extraordinary.
A constant battle against prejudice.
Truly.
And we have to touch on the ethical questions. Her discoveries brought medical marvels, but also opened the door to destructive power.
It's the classic dual-use dilemma in science. Knowledge itself isn't good or bad, but its application can be. Her work forces us to confront questions of scientific responsibility, questions we still grapple with intensely today.
And the personal cost. The health risks.
Yes, the tragic irony. Working so closely with highly radioactive materials without understanding the dangers?
Carrying samples in her pockets, keeping them by her bedside.
Fascination outweighed caution, and the long-term effects weren't known. It led to chronic illness, likely aplastic anemia, which caused her death in 1934.
A stark reminder of the importance of safety protocols that her work, ironically, helped necessitate.
Definitely. Her notebooks, even their cookbook, are still radioactive today, stored in lead-lined boxes.
Wow. But despite everything, she became this incredible icon. And the legacy continued with her daughter, Irene Joliot-Curie.
Who, along with her husband, Frédéric Joliot, won the Nobel Prize in Chemistry in 1935 for discovering artificial radioactivity. An amazing scientific family dynasty.
So, summing up Marie Curie's impact, it's monumental. She didn't just change chemistry and physics by discovering radioactivity and new elements.
No, her work fundamentally altered our view of matter and energy, and implicitly, as we've discussed, laid crucial groundwork for quantum mechanics. Those concepts, like the probabilistic nature of decay, quantization of energy.
They feed directly into things like qubits for quantum computing.
Absolutely. Qubits rely on quantum phenomena like superposition, existing in multiple states at once, and entanglement, linked fates of particles. Understanding the quantum nature of matter, which Curie's work necessitated, underpins our ability to even conceive of, let alone build, quantum computers.
And for quantum sensory.
Her insights into how matter interacts with radiation and her development of precise measurement techniques are fundamental. Quantum sensors leverage subtle quantum effects to make ultra-precise measurements of time, gravity, magnetic fields. It's all built on that deep understanding of the quantum world she helped reveal.
And her whole approach for fundamental interdisciplinary research that remains a guiding principle.
Absolutely, a beacon for how science should be pursued.
So maybe a final thought for you, our listeners, to consider. Marie Curie's story is this powerful reminder, isn't it? That exploring fundamental questions just out of sheer curiosity, even when you can't see the immediate payoff.
Yeah, that patient, rigorous exploration.
It can end up completely revolutionizing everything in ways no one could have predicted at the start. Her spirit, facing down scientific and societal barriers, it's just incredibly inspiring for anyone pushing boundaries today.
Well said.
Thank you so much for joining us on this deep dive.
My pleasure.
And our thanks again to Yorgo Schneepat for the essay that guided our conversation today.
A really valuable perspective.
Definitely. We encourage you to explore more at schneepat.de. That's SCHNEPPAT.de.
Check it out.
Until next time, stay curious.